You want a lab exam? We can make
In this
that
class,
happen.
that'd be fine.
Oh yeah, all right, great.
But not like a
Let's do it.
maple lab exam, or just like
Those were so easy.
I love lab exams. They're just like the chillest thing ever.
Oh, well, we can do a different style of lab exam.
Wait, what do you feel like?
It's not in the syllabus, so we won't do it.
This is one of our lab exams got canceled because Robert got sick.
It happened for us too.
Yeah.
He got sick.
In 121, he got sick. He told us he canceled the lab exam, but instead of canceling the lab exam, he cut a week from our individual project.
Oh, that's no.
Yeah.
Our teacher was amazing.
Yeah. Love Robert.
Great.
Did you like Flora?
Well, Robert
We had Robert for our last. Yeah, who did you let him from?
Oh, Amir.
Oh, we got heard about the rest of that class.
It's great.
Good.
Yeah, I heard he was the only one that was willing to cut it.
I would take it possibly.
I think the one issue is just those on my goals. It's just I think they're fair. I just think like he would take like questions from an anchor just so I didn't match them with
All right, so I think we're ready to get started here. So, what we were talking about last time is we began our discussion of error analysis. We're going to touch the topics that will be useful for you in the Phys 231 lab as you take data from the circuits. So far, we really haven't done too much data collection in lab 1, but in lab 2, we'll start with verifying Kirchhoff loop laws and junction rules. So the scenario we imagined was pretty simple. We thought about dropping a coin from a building, and we repeat that measurement over and over again, and then we plot a distribution of the data as a histogram. And what we argued is that we would expect to get something like these black bins here. And in the limit that we took a very large number of measurements, that distribution should approach a Gaussian distribution, which I've tried to draw as this green line. So to characterize the Gaussian distribution, there's two quantities that we can use. One is the mean, where we just add up all the individual measurements and then divide by the number of trials. And that should find the center of the distribution or the peak. And so we'll label that as mu. And then, of course, to calculate that average value is just sum up all the different times from each trial, divide by the number of trials. The other thing we could characterize is the width of the distribution. And we're going to call that sigma for the standard deviation. The standard deviation squared is given by the sum of the individual measurements. I guess I should, if I'm going to use t for time, I should be consistent here. So let's say this is time, ti. We take the difference between each trial and the mean, we square that, and then add them up, and then it turns out you divide by n minus 1. So in that sense, for large n, this is like the average of the square of the deviation. The reason it's squared is because if we didn't have the square there, if we just took the difference between the trial and the mean, sometimes that difference would be positive, sometimes it would be negative. And when we added them all up, they would sum to something that's close to 0. So by squaring it, we're adding up only positive quantities, and so we'll get us a non-zero result. That non-zero result gives us the width of our distribution. Now, I'm not going to justify it, but it turns out that for a Gaussian distribution, we should expect that 68% of our measurements should fall within one standard deviation of the mean. So if our Gaussian distribution was normalized so that the area under the curve was 1, so if we calculated the area underneath this green curve, it would be 1, then this blue shaded area that is between the mean minus a standard deviation and the mean plus a standard deviation would have an area of 0.68 or 68%. Okay, so then what we want to do is we want to think a little bit about collecting data and what this distribution would look like in different scenarios. So the first thing I'm going to say is that if we were to measure a quantity n times using the same experimental setup, then what we should report as our best estimate of the true value of that quantity, whether it's the time for the coin to fall or whatever it is just given by the mean. So the mean is what we should report. The same experimental setup, then our best estimate of the quantities true value is the mean mu. All right, And so what I want to imagine is that we do this sort of experiment, and we measure these distributions. And so let's suppose that I go up to the building, I drop the coin, and I do 10 trials, and then I report the mean. And then you go up and you do the same experiment, but you do 1,000 trials, and then you report the mean. Who do you think has the better estimate of the true value? Someone who's done a few trials or someone who's done a lot of trials? A large amount of trials, right? That's intuitively fairly obvious. So let's just write that down. We expect our estimate of mu to improve when we increase the number of trials n. Oops. The number of trials n. Okay, and so what I want to do is I want to show you some plots of some simulated data. Okay, so on the course website, there is, I'll show you where it is. There is a link to error analysis slides. It says it would be shown in the first week of classes, but I reordered things a little bit. So anyways, here are those slides. And the first slide is what I'm going to show you is 50 trials of an experiment where the mean has been set to be 150. So if this was dropping our coin, I'm assuming that the true value is 150 seconds. And so here is one distribution for 50 different trials. And you can see it kind of has some of the features of a Gaussian distribution. It's kind of symmetric. There's sort of a peak, although the tallest bins are not in the center. So it has some features of a Gaussian distribution, but it doesn't really look like a perfectly smooth one. So all I'm going to do is I'm going to show you more plots here where we're going to increase the number of trials. So here we're going from 50 to 100. And so the green data is, imagine doing the exact same experiment, just do it 100 times. And we can see that, well, this is starting to look a little more like a Gaussian. It's a little more symmetric. And now the tallest bin is closer to the center. And then we just keep going. And so now here is 200 trials. So we doubled it and then double it again. And the blue data is looking even more Gaussian-like. The peak's a little more well-defined. And of course, we can just keep going. And so here is 400, 800, 1600. So each time we're increasing the trials by a factor of 2. So specifically, this one with 1600 trials is 2, 4, 8, 16, 24 times more trials than the red one. And so by the time we get to 1600, that's looking fairly Gaussian-like. Yeah.
I'm just curious, so will the Gaussian always apply, even if there's some intrinsic error in our measurements? Like if 150 was the correct amount of, the correct quantity,
yeah,
but we have some error that was making it so that skewing it to 160, for example.
So like a systematic error? Yeah.
We'll still always see a Gaussian? It will just
you'll still see the Gaussian, it'll just be shifted to 150. And so if you have a systematic error like that, where it biases your measurement always in the same way,
yeah,
you're not gonna be able to detect that just from the data. You have to know about your experimental setup and know that it's susceptible to some problem.
Yeah.
So if you're blind to that, you're just gonna miss it.
Yeah.
Yeah. Yeah.
So there's never some exception where we won't see a Gaussian error?
So you won't see Gaussian if the uncertainties are not random. So if they're not distributed symmetrically about the average value. Yeah. 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 So most often we will see a Gaussian, but it's not guaranteed to 100% of the time. All right. So in this next slide, what I'm going to do is I'm just going to take all of these Gaussian distributions and I'm going to overlay them on top of one another. So this one will, I think, be in the back, and then this will be on top, and then on top, and so on. I think that's the next slide. Yeah, there it is. And so the question I have, let me hide some of the writing there. The question that I have is, how do the widths of these distributions change as we increase the number of trials? So, for example, this green one is 100, this blue one is 200, this cyan one is 400. So what's happening with the width of this distribution as we increase the number of trials? It's more narrow. Why do you say more narrow? So yeah, I mean, you have some expectation, but what does the actual plot show us? It gets wider. So, I mean, you could say here's the 51 is a little narrow. I can see the other ones behind it. Is it getting wider by a lot? No. We've increased the number of counts by like a factor of 24. And certainly nothing here is 24 times wider than anything else. Yeah. Anyone else have anything? Yeah.
I guess the peak narrows and the base kind of widens because there's more chances for outlier.
Yeah, I don't know. I don't see that. I mean, what I see is that all of these distributions more or less lie on top of one another. Of course, there are differences, right? Each of these plots is not identical. Sometimes we have a tall bin here versus a short one there. But like we've made a large change to the number of trials, yet the width or the standard deviation is not changing much, if at all. In fact, like if you want to say that the red one is more narrow than the others, then we should expect to see this brown one with 1,600 trials should be wider, and we should be able to see it, but it's not. We can't see any of the brown one. And so there is no systematic way in which this width is changing as we change the number of trials. And so the takeaway from this is the standard deviation or the width of the distribution is independent of the number of trials we make. And so that's an important thing to realize. Now, we expect that as we increase the number of trials, our estimate of the mean should be improving. And one way to see that is to go back to the series of plots. And, if I look at some of these that have a low number of trials, and I ask you to identify exactly where is the peak, well, that's hard to say, especially for this red one. I want to say the peak is in the center, but the two tallest bins are off center. Here, it's a little easier, but there's sort of 3 or maybe 4 bins that are all fairly tall. And so which one is exactly the peak is hard to know. But here when we have a large number of trials, the thing is very symmetric. There's kind of 2 peaks equally tall, and we could identify the center as sort of being right between those 2. And so it's clearly easier for us to identify the position of the peak or equivalently the value of the mean when we have a large number of trials than when we have a small number. Yet the standard deviation is not changing. So what that means is that the standard deviation by itself is not going to be a useful measure of our uncertainty about the mean. So we're going to have to think a little more carefully about how that will all work. Okay, good. So let's write some of that down. All right. So we say, however, the standard deviation is independent of the number of trials n. And so therefore, the standard deviation sigma by itself is not a good estimate of the uncertainty in the mean. Okay, we can understand this statement that the standard deviation is independent of the number of trials if we just go back and look at our definition of the standard deviation. This is the square of the standard deviation. So if you like, you can put a big square root around all of this. But let's just try to understand that. As I increase n here, I'm going to increase the number of terms in my sum. And so this difference squared is always positive, right? I square a number, it always has to be positive. So as I increase n, I'm adding more and more positive numbers together. And so the value of my sum is increasing. But I'm also dividing by n. And so those two effects compensate for one another. So as n increases, the sum gets bigger, but I divide by a bigger number. And so you end up getting the same value. What that tells us is that this standard deviation, how wide our distribution of measurements is going to be, is determined not by the number of trials, but on how your experiment is being conducted. What is the method that you're using to make those measurements? If I drop the coin from the building and I'm using just reaction time and stopwatches and talking to someone on the ground with a cell phone, then that's maybe not the most accurate way to make these measurements, and I'm going to end up with a wide distribution. If I go set up something sophisticated where my coin passes through some beam of light and triggers starts and stops of a clock, then I can get more precision in my measurements and the width of this distribution would go down. So standard deviation is determined by the experimental setup. The standard deviation is determined by experimental setup / measurement method. Measurement method. So that means to decrease sigma, we need to improve our experimental procedures, setup / procedures. Okay, so let's suppose that we've done our setup, we're satisfied, like we can't make any more realistic improvements, we've designed it the best we can. Sigma is going to be what sigma is going to be. So what then how should we estimate the uncertainty in our mean? Okay, so what I want to do is I want to go back to these slides here. Okay, and so here is a series of measurements of 100 trials of the same experiment. So this is all the thing where we expect the mean to be about 150. And so we imagine we go up on this building, we do 100 trials, and we calculate the mean. Then we do another 100 trials, calculate the mean. Do another 100 trials, calculate the mean. Like in practice, you would never do this, but let's imagine we did. So from the first set of 100, we get a mean of 150.1. For the second trial, we get 150.37, 148.75, 149.56. We get a slightly different average value every time. Of course, we'd expect that because it's a set of a different 100 trials. Even though the experiment is identical, the actual data that we collected is different. So what are we going to do with this? What I want to think about is, let's do this 100 trials, calculate the mean, like 1,000 times. Okay, so we're going to do this set of 100 measurements 1,000 times. So we end up doing something like, what's 100 times 1,000? 100,000 different trials. But we're going to break them up into these sets of 100. And we're going to take the mean values, we would have 1,000 of them, and we'll plot a distribution of those means. Okay, and what it would look like is the following. The green distribution is just one set of 100 measurements. It's the exact same plot. It's this one in the top left corner. So that green one is just, I'm just repeating that set of 100 just as a comparison. And then this narrow distribution is the 1,000 values of the mean. And you can see that it has its own width that's just much less than the width of the green set of data. Okay. So it turns out that the width of the means, the standard deviation of the means, is equal to sigma divided by the square root of n, where n is the 100 trials of each set of 100 that we did. So as we increase n, this value, sigma divided by the square root of n, goes down. And that, it turns out, is our uncertainty in the mean. And that's called the standard error. Okay, so let's jot that down. So the proper estimate of the uncertainty in mu is given by the standard error. And we're going to denote that, we're going to use the notation sigma subscript mu. So this notation is supposed to remind us that this is an uncertainty. It's related to the standard deviation, but it's not the standard deviation exactly. And then the mu is telling us that this is the uncertainty in the mean. And it is given by the standard deviation divided by the square root of n. Okay, so let me write that here and I'll label the various things. So this is our standard deviation. This is called the standard error, or the uncertainty in the mean. And n is the number of trials. So this has the feature that we like, where when you increase the number of trials, the certainty or your confidence in your estimate of the mean, it gets better because the uncertainty decreases. The square root tells us that it's not proportional to 1 over n, but 1 over the square root of n. So if I want to cut down my uncertainty by a factor of 2, I have to not double the number of trials. I have to go up by a factor of 4. If I want to get this down by a factor of 10, then I have to increase this by a factor of 100. That's why, like, a lot of these experiments we're doing, like, say, discovering new particles at CERN or something, like discovering the Higgs boson. When they're trying to get their uncertainties down, what they have to do is they have to increase their trials by a lot. So that's why they do so many repeated collisions over and over and over again, is if they need to get their uncertainty below a certain threshold, they might need millions of counts or something like that. And so that's why they just keep doing these trials over and over and over again. It's all about reducing the uncertainty so that they can have confidence in reporting whatever discovery they've tried to make. I know this is not very satisfying where I just tell you what the answer is, but next week, what we'll have is we'll have enough knowledge that we'll be able to go through a more of a mathematical argument to justify this expression. So that's coming next week. All right. So sigma mu has the desired property that it decreases as the number of trials n is increased. Okay. So in summary then, when we repeat a measurement n times, the final result that should be reported is the average value, mu, plus or minus the standard error, which is the standard deviation divided by the square root of n. Okay. So that's one thing I wanted to cover. The next logical question is, look, maybe we've measured something, some quantity, and then we want to use it to calculate a new value. Well, the new value is going to be calculated from something that we've measured that is uncertain. So it stands to reason that the calculated quantity would also have some uncertainty, and we want to understand how to propagate that error into our calculated quantity. For example, this might be like, I don't know, the measurement of a temperature, and then you're going to go and say, all right, I'm going to now calculate resistance based on that temperature, right? I know the resistance of my resistor is a function of temperature. It increases as I heat it up. And so I'm going to calculate the resistance based on this measurement of the temperature. What is my uncertainty in that calculated value? So that's the next topic. If we measure, say, X, I think I missed the page. If we measure X plus or minus sigma, let's say just delta X, some uncertainty, then what is the uncertainty in Y is equal to f of X, i.e., we calculate Y based on the value of X. What is the corresponding uncertainty of Y? Okay, well, this is going to turn out to be kind of, I think, fairly easy to answer. So what I'm going to do is I'm going to plot here the function of X. So this is f of X, so that's also what we're calling Y on the vertical axis, and X is on the horizontal axis. I don't particularly care what this function looks like. I'll just draw something. And let's suppose we go do our experiment and we find that the value of X sits right here. So we went and we measured X and it sits right there. So this is going to be our measured value of X. Okay, before I do anything else, there's some uncertainty associated with this value of X. And so I'm going to label that on our plot as well. So we're going to have X plus delta X is sort of like our upper limit of the range of reasonable values. You know, usually our uncertainty hopefully would be small, and so it would be kind of closer in here. I'm going to exaggerate it just for this drawing, for a bit of clarity in the drawing. And then down here is going to be x minus delta x. Okay, based on what we just talked about for Gaussian distributions, we should expect that, you know, most of our measurements would fall between these two limits, these two ranges. All right, so the first thing I'm going to imagine doing is I'm going to draw a line that's tangent to this curve right at x, our best estimate of the uncertainty. So we'll have a point here, and then I'm going to draw a tangent line. What's the slope of this tangent line? How do I calculate this slope of this line? Yeah, that's right. So this is a tangent to f of x at x. The slope of this line is df dx. Okay, well, what I could do is I could use this slope to estimate by how much does y change if I allow x to span this range that is 2 delta x wide. So this range is 2 times delta x. And what we could do is we could find, where does this dashed line intersect our tangent line? Well, that's going to sit at some position we'll call y minus delta y, right? It's the minimum likely value for y. Over here, right at the center, we would have our calculated value of y if we think x is the best estimate. And then up here, we would have y plus delta y, which is the maximum likely value of y. And so there's a certain range of y values here. This spans 2 delta y, right? So if I just take the difference of these two, I get 2 delta y. All right. And so if you think about this a little bit, we now have a relationship between 2 times delta x and 2 times delta y. This is like the run of our green line. And this is the rise of our green line. And the slope is rise over run relates these two. So the slope is equal to df dx, which is also just rise over run. And our rise is 2 delta y, and our run is 2 delta x. So cancel, cancel. And let's just solve for delta y. So delta y is going to be equal to, actually, let me call, since f is equal to, we said y was equal to f of x, I'm going to call this dy dx. I think that will be better. So let me make that same change over here so that it's consistent. All right. So this is going to be dy dx times delta x. Now, in general, we could have a negative slope, right? If I chose x over here, my slope would be negative, and I would go through the same sort of argument, and I'd get the exact same result. But usually, well, not usually, always, we report positive quantities for uncertainties, understanding that the range is between plus and minus delta y. To get a positive value all the time, we can put an absolute value sign around this slope, the derivative. And so here it is. So if we know x plus or minus delta x, and y is a function of x, then delta y is the uncertainty in y. Okay, so that's not so bad, right? That makes some sense. We're gonna try to extend this a little bit more. And the way we're gonna do that is we are going to imagine, all right, what if I have a quantity that depends on two measured values? I'm gonna measure x1 plus or minus delta x1, and then I'm going to measure x2 plus or minus delta x2, and I'm going to calculate some quantity that y is some function of both x1 and x2. What then is the uncertainty in y? Okay, so let's go back and look at these slides. I think I've got one more little set here. Okay, so here's some more simulated data. The mean, again, is 150. This time, I've done 1,000 trials and 1,000 trials. And what we're going to do is we're going to add these distributions up. The way it's done is I'm going to take trial 1 from this set of 1,000 measurements. I don't know where it is. Maybe trial 1 was at like 145. And then I'm going to take trial 1 from this set of 1,000. Maybe that was up at 165. I'm going to add them together, and that will make a quantity in this distribution. If it was, what did I say, 140 plus 165, that would be sitting at 305. And so that one would be sitting right here. That one's near the peak because here I chose one that was below the mean, and here I chose one that was above the mean. And I do it for trial 2. If trial 2 is 130 here and 140 here, I would add them up and I would get 270. And that one would be sitting over here near the tail. And I just do that for all 1,000. And after I've done that, I plot that distribution of 1,000 summed trials. And I get this distribution. What I'm interested in doing is taking the width of this set of 1,000 measurements, the width of this set of 1,000 measurements, and comparing them to the width of this summed distribution. Yeah.
How exactly do you measure the width, like for the standard, to figure out the standard deviation?
Oh, yeah. So it would just be the it's the xi minus mu squared, sum them all up, divide by n minus 1. So you just, from your trials, you can just calculate the standard deviation, right? It's just the normal standard deviation calculation. Yeah, yeah. So what I'm going to try to show here is that this purple distribution is clearly wider than these two individuals. But it's not what you would naively might think. It's not double the width of those two, right? This black arrow is the same size as these two black arrows. And here's two of those black arrows back to back. And this green arrow is the same size as this one. And you can see that this green arrow is somewhere between 1 and 2 times the standard deviation of the original sets. It turns out that this is given by the square of the width of one distribution plus the square of the width of the other distribution, then square root all of that. And that's called a quadrature sum. I can't justify for you where this comes from right now, but if you take 232 next term, we will do that in that class. Okay. And so here is just basically repeating the same data. Here's one of those 1,000 count spins. And so there's that width, and it's shorter than the width of the sum distribution, but it's not half of it. Okay. So All right. So I think I want to make some comments about that, and then we'll answer the question that we asked in the notes. Okay. So if we measure x1 plus or minus delta x1 and x2 plus or minus delta x2, then what is the uncertainty in y is equal to x1 plus x2, i.e., what is delta y? Well, it turns out that delta y is given by it's called a quadrature sum. Quadrature sum of delta x1 and delta x2. And the way that sum works is the uncertainty in y is the uncertainty in x1 squared plus the uncertainty in x2 squared square root. Note that this is less than delta x1 plus delta x2. If you were in a first year lab, like last year or something like that, and you summed two quantities that had uncertainties, what you would report is the sum of uncertainties for the error in x1 plus x2. That turns out to be an overestimate of the true error. And the reason it's an overestimate is because when I take two measurements, there's some probability that one of the measurements is going to be a little bit below the mean and one's going to be a little bit above. So when you add them up, there's this like self-compensation. That's why this quadrature sum is used and is less than this total sum. Okay, does that make sense?
What you're saying, not just like something experimental.
Yeah, 232 will do that. We'll do a rigorous derivation of that. Yeah. Okay, so now let's go. How much time do we have here? 8 minutes. Okay, good. So we can finish this one next little thing. So now, suppose we measure u plus or minus delta u and v plus or minus delta v, and we want to calculate y is some function of u and v. Okay, so what is delta y? Well, what we're going to do is we're going to use the previous results that we've just kind of worked out. If we had just a function of one variable, we would take the derivative of y with respect to u and multiply it by delta u. Or if it was a function of just v, we would take the derivative of y with respect to v and multiply by delta v. But in this case, we're going to have both those contributions. And so we want to combine them. And we'll combine them using this quadrature sum method. Okay, so the strategy is to first we find the uncertainty in y due to the u variable. So I'll call that delta y sub u. And that's going to be the derivative of y with respect to u times delta u and delta y v. Sorry, okay, let me slow down here for a second. Let me ask you this question. How have you seen partial derivatives? Are you doing that now? Yeah, you're doing that now? Okay, good. So let me just remind you that if you have a function of multiple variables, partial derivatives are nothing confusing, right? All you're going to do is say, okay, y is a function of u and v. For the purposes of this derivative with respect to u, I'm just going to assume that v is a constant. And then I just do an ordinary regular derivative, okay? We'll do some examples. We're going to run out of time today, but we'll do examples on Monday, okay? So that's the first step. Then we find the contribution to delta y due to the v variable. And it's exactly the same. Delta y due to v is going to be the partial derivative of y with respect to v. We'll put an absolute value sign so we get a positive. And then we multiply by the uncertainty in v. All right. And then the last step is finally, we combine the two contributions using the quadrature sum. So delta y is equal to, let's see, delta y u squared plus delta y v squared. We have our two contributions. Oops. Like so. And then if we put in the actual derivatives, what we end up with is dy du delta u squared plus dy dv delta v squared. And so that is how we would do it for a function of two variables. But of course, if I had a function of three variables, say u, v, and w, I would just have a delta y w term in here. So it'd be plus delta y w squared all under the square root. And delta y w would be dy dw times delta w. So you can generalize this to as many variables as you want. So in general, for a function of any number of variables, y is some function of x1, x2, all the way up to xn, where n is as large as you want, then delta y is going to be, sorry, I keep writing df, dy dx1 delta x1 plus dy dx2 delta x2 plus and so on plus dy dxn delta xn. And so what I have to do is I have to make that a quadrature sum. So I'm going to square all of these. And then I'm going to square root everything. And this is propagation of errors. And this is what I want you to use when you, oops, let's see. Make that look a bit better. This is what I want you to use when you are calculating quantities based off of measured values that have uncertainties. And we're going to do examples on Monday. But one thing that I like about this is that, well, there's two things that I'll say. One is I don't have to remember a bunch of different rules for different cases. So in first year, if I add two quantities with uncertainty, then the uncertainties add. Or if I add or subtract, the uncertainties add. If I was doing multiplication or division, I have to remember that I have to add the percent uncertainty or the fractional errors. If I'm doing powers, I have to remember that it's going to be the fractional uncertainty times the value of the power. And so that's kind of annoying to have to memorize all these silly rules for different cases. And on top of that, if I have something that's not covered by the rules, then I'm in trouble, right? What if y is equal to f of x? Sorry, y is equal to the sine of x. I don't have a rule for trig functions, so I don't know what to do. What if y was equal to the ln of x or e to the x? I don't have rules for all these functions. But we will find that this propagation of errors covers all cases. It covers addition, subtraction, multiplication and division, powers, functions like trig functions, logs, exponentials. As long as you can actually evaluate the derivative, this will always work. And so I want you to forget about all the rules and remember this one thing that covers all cases. And we'll do examples on Monday. All right. No, I mean, I'm not saying that that could never happen, but it's extremely rare. Yeah, we're going to do examples and then we're going to get back to electronics. Yeah. Perfect. Okay.